Now let us consider example 1 that we have a circuit that contains an unknown source. That is, we could have an ideal voltage or an ideal current source. And that source is connected to a resistor R. Now, we are able to vary R between a value of 0 and infinity, and we can measure our voltage potential established across R by placing a voltmeter at terminals A and B. And we can also determine the current running through a resistor by either placing an ammeter in line with our circuit in our resistor, or using Ohm's law. Now, say we collect data experimentally when we vary our resistance from 0 to infinity. That is, we measure our current and voltage, and we have the following data. We notice a few unique things. The first is when our resistance is set equal to 0, we have a short circuit. That is, our current can flow through a trace between A and B unimpeded, such that our voltage potential would be equal to 0, and our current running through it would be I sub SC, standing for short circuit current. Now, as our resistance tends to infinity, what we notice is our current is going to tend to 0, and our voltage potential is going to reach a maximum. That is, when R is equal to infinity, we have our open circuit voltage. That is, our circuit is connected to terminals A and B, and no current is running through our resistor such that it appears to be connected to nothing. Our open circuit voltage is designated as V sub OC. Now, interestingly, if we plot our data, our voltage versus current, we see that when our current is at a minimum, our voltage is at a maximum, designated as V sub OC, and then as our current is at a maximum, our voltage is at a minimum. And we have a linear relationship where we can determine our slope, our rise per our run, where our rise would be the change of our open circuit voltage, and our run would be our change of our current. Now notice we have a negative slope within this system. For a linear equation, we apply the following. Y is equal to mx plus b, where m is our slope and b is our y-intercept. Solving for our slope, we would have our rise, which is the negative of our open circuit voltage, per our run, our short circuit current, which gives us a value of minus 24 volts per 3 amps. Or this would be negative 8 ohms, and we will designate this as R sub T, our Thevenin resistance. Now, to determine our y-intercept, we set our current equal to 0, i.e. x, and solve for y. We see when our current is equal to 0, our output voltage is 24 volts, which is equivalent to our open circuit voltage, which takes the placeholder variable V. Such that if we construct an expression for our voltage, we'd have minus 8 ohms times our current plus 24 volts. Or in terms of our Thevenin resistance and open circuit voltage, we have the following. Our voltage potential across our resistor would be equal to the negative of our Thevenin resistance times our current plus our open circuit voltage.